Hi guys, Mark here and welcome to day 13 where we'll be solving the 13th pair of puzzles in the Advent of Code challenge. And we've made it over halfway, which I'm really pleased with. I was a bit worried that maybe I wouldn't be able to solve all of the challenges, but so far so good. And in fact today's one was a little bit of a kind one because it's a variation on a puzzle that we've solved already. If you remember, on day 9 we had to solve what was the best route for Santa to visit all of the cities. And so it was kind of an optimal travelling route, or the travelling salesman problem, as it's sometimes known. Well, this is an optimal seating arrangement where you have some people sat at a circular table and you need to work out what seating arrangement would maximise the happiness of everyone. And we've got this input that basically tells us how happy every person would be to sit next to every other person. And of course, unlike the travelling Santa problem, this is a two-way relationship. So Alice might be happy to sit next to Bob, but maybe Bob doesn't want to sit next to Alice. And so there's two-way relationships in the input. But apart from that, it's going to be very similar. Basically, we need to calculate all the permutations of ways we can arrange people at the table, score those permutations, and then pick the happiest one. So let's have a look at the code. And first of all, as usual, we'll see how I solved it in C#. So no real surprise that I started off with the test input. And that's usually a good idea, particularly on a problem like this with permutations. The test input will just run a lot quicker. Although, thankfully, in our real input, there weren't loads and loads of people at the table. There were about 8 people, I think, at the table. And what I do is I use a regular expression to parse out all of the relevant parts from each line. The two names, whether it's a loss or a gain, and how many happiness units. And again, regex.match doesn't really play very nicely with LINQ. You have to go through this rather convoluted transformation to get the groups, cast them into a strongly typed enumerable of group, skip over the first one because that just matches the whole string, and then select the value of the group and turn it into an array. So a little bit of a pain, but once we've done that, we can pick out the two names and the gain, happiness gain amount, whether it's positive or negative, and parsing the integer. So once we've worked out these rules, we can get a list of all of the distinct people. So that's just selecting the names from the rules and calling distinct on them. And we can also make a dictionary to look up for every pairing what would be the happiness. And there's a few ways I could have done this. I chose to use as a key the two names with a dash between them. So the key will actually be Alice-Bob and Bob-Alice, with the integer gain amount as the value of the dictionary. And I'm able to use this nice C#6 string formatting syntax, which just makes our code a little bit more succinct. Now, for part B of the problem, you can see I've got a couple of lines here. For part B, you add yourself to the people at the table. And so I just threw myself into the dictionary, and you don't care who you sit next to, and no one cares if they sit next to you. So the values are all 0. But then we're ready with this lookup dictionary and list of people to work out the permutations and score them. And this is really where MoreLink is going to come in fantastically useful. If you watched my day 9 video, you'll know that I used an alpha pre-release version of MoreLink, which has got this permutations method, but we're actually going to use 5 methods from MoreLink in this solution. So one of the things I realized was I didn't actually need all of the permutations. If you think about it, a seating plan A, B, C, D is actually exactly the same as a seating plan B, C, D, A. And that's because this is a circular table. And so many of the permutations would just be the same seating plan. And so to optimize it a bit, I skip over the first person and I range everyone else in every possible way around that one person. However, that does mean that after I've got the permutations, I need to put the skipped over person back. And so I can do that with a prepend MoreLink method to add the first person back onto the sequence. And I also add the same person to the end, and I do that with morelinks concat. And the reason I add them to the beginning and end is so that when I use morelinks pairwise method, I'm going to get every pairing in the entire table. And so what pairwise does, if you pass it a sequence A, B, C, D, it will give you A, B, B, C, C, D. And that's why I needed to put the first person at the end as well, so that I would also get DA. So once I've got all of the pairs, then I select an anonymous object because I decided I'd like my output to show us what the seating plan is. That wasn't actually part of the problem, but I thought it'd be interesting to see. And calculate the happiness by adding together the looked up values for that pairing. And we have to remember that we are looking at both ways. So if Alice is sitting next to Bob, we must look up the happiness for Alice to Bob and Bob to Alice. Almost said blob there. And add them together. And because I've selected this anonymous object, I can't just use max. And so Morelink to the rescue again, I can use max by to return the object that has the highest happiness value. And so if we run that, we see it runs relatively quickly and I get my happiness amount. It turns out that I actually make people less happy by sitting at the table with them, which I guess is probably true to real life. Anyway, moving on quickly, let's have a look at how I solved this in F#. Now in F#, a large part of this is pretty much the same. We're still parsing each line in the rules with a regular expression and having to jump through some hoops to get it into a nice format. But then I turn each rule into a tuple of a tuple and an int. And the first tuple is the two people's name, Alice and Bob, for example, and the int is their happiness amount for that relationship. And the reason I do this is because this makes it very easy to turn these rules into the lookup dictionary, and we'll see that in just a moment. And so I parse each of the rules in the input and I put that into a rules list. Then again, we are going to need to do permutations. And as on day 9, I made use of John Harrop's permutation F# function because it's really nice and elegant. And so that's what I've decided to use again for this puzzle. And then I made a method called find the happiest seating plan. And I did this so that I could solve parts A and B without having to modify any code. And so we just pass in the rules and we find the happiest seating plan. So what do we do in this method? Well, we start off by getting all the distinct people. That's the same as we did with C#. We're just looking through the rules and picking out distinct names and putting them into a list. Then the lookup is nice and easy. We just take those rules and put them into a dict, and we can do that nice and simply because they're already tuples of key to value. And this dictionary, unlike the C# version, is keyed on a tuple because it's much easier to do that in F#. However, to help me solve part B more easily, I wrote this get pair happiness, that you pass in a pair, say Alice and Bob again, and if they're in the dictionary, then we work out the happiness of both ways around of the relationship. And if they're not in the dictionary, we return 0. And of course, when I add myself to the list of people, I won't be in the dictionary because I wasn't in the rules list. And so now we're going to take a very similar approach to what we did with C#. We'll save the first person in the list, and you can do that by saying list.head, and then take all the rest of the people, that's people.tail, calculate all the permutations, and then we're going to work out the happiness of those permutations. And again, because I'd like my output to show the seating plan, I'm going to return a tuple that has the seating plan, which is basically the permutation with the first person just tacked onto the beginning. And then I need to actually work out the happiness of this seating plan. And so to add a person to the beginning and end of a sequence, like we did with C#, I can do that by creating a sequence expression, yielding my first person, yielding all the people in the permutation, and then yielding the first person again. And then F Sharp has got a pairwise function, so I can just pipe that into that. And F Sharp has also got a sum by function, so I can pipe into that and call the get pair happiness on each of the pairs and sum together. And like Morelink, F Sharp has got a max by, so I can just say find me the max by the second element of the tuple, which is the happiness for that permutation. And so this allows me to pass my rules into the find happiest seating plan to solve part A, and to solve part B I just add an arbitrary rule to my rules list of myself to nobody has a happiness of 0, just so that I'm included in the list of people. Append that to the beginning of the rules and call the method again. And if we run that, we will see we get the same results as we do in C#. By the way, you might notice that I have in comments the answers to my puzzles, and that's because I do a lot of refactoring, and I always want to make sure that I haven't accidentally broken something while I'm doing the refactoring. By the way, another thing I've discovered, although I'm a huge LinkPad fan, LinkPad really isn't the best for writing your F# code, because you don't get all of the great tooltips that you get in Visual Studio. If you hover over a function, you don't get to see what the compiler has inferred the type of that function to be, for example. So, as I said, although I'm a big LinkPad fan, for working on F# code, I think Visual Studio is currently better. Anyway, that's all I have for today. Hopefully I'll see you tomorrow. Thanks for watching.